morning. Welcome back to the course Engineering Metrology, and I am taking Statistics in Metrology part in this course. So, this lecture will continue the probability distributions. Next, I will move forward to Chi-square distribution. What is Chi-square distribution? We have already discussed how different finite sized data sets of the same measured value would be somewhat different statistic. We can estimate how well the standard deviation of the sample predicts the standard deviation of population. This is for sample, this is for population. So, when we do not know the value of mean, when some value of mean is not given and we are just working with standard deviations, the Chi-square distribution is more useful. So, because it can make the estimates based upon the standard deviation of samples only. So, if we plot the sample standard deviations for many data sets, each having n data points, let me call it n data points, okay, there are many data sets, we would generate the probability density function of P Chi-square. Probability density function of P Chi-square is again skewed like this, probability of Chi-square, and it depends upon the degrees of freedom. Degrees of freedom plays a great role here. Degrees of freedom is actually when we have n data points and data sets, degrees of freedom is equal to V is equal to n minus 1, and when this n minus 1 value is 1, the distribution is somewhat like this. Okay. This is equal to, this is for V is equal to 1. When this is equal to 3, that is 4 samples, this is for V is equal to 3, and we have equal to 10 somewhat like this. This is for V equal to 10. So, this is probability for Chi-square and this is Chi-square. This is Chi-square in this direction. Now, what we are interested in? We are interested in finding the value of Chi-square, and to just we need to see that is the data or the sample that we are talking about, does that sample, that the standard deviation predicts the population standard deviation or not. This is actually the key to use Chi-square distribution. Does the sample standard deviation predicts the population standard deviation or not? Okay. Now, this is the distribution of Chi-square in a tabular form. We have degrees of freedom V is equal to n minus 1, and Chi-square can be calculated as a ratio of the sample and the population variances. This is equal to mu Sx square over sigma square. Please be careful here that I am putting sigma for population, not for sample here. For sample I have put the value Sx. The sigma is the population standard deviation and Sx is the sample standard deviation. I am interested in finding the value of the probability whether is my sample significant or not. Now, I am talking about the word significant here. So, this I like to talk in normal distribution as well. I discussed this before also. When we have, let me say 3 sigma minus 3 sigma and plus 3 sigma, we had 99.7% area here, okay, or let me call it 2 sigma, okay, 2 sigma I have 95% area here to keep it a little simpler. So, this is 2.5% here and 2.5% here. So, that means when I am selecting 2 sigma limits for my to see the credibility of my sample, 2 sigma limits means I am 95% confident. If it is within 3 sigma limits, I am 99% confident. If I am 95% confident within 2 sigma limits, that means my significance level in case of two-tailed test, considering two-tailed, it is 2.5%. In case of one-tailed test, we need not to go into the depth of these things. In case of one-tailed, it is somewhat like this. If this is 95%, this 5% is the significance level. So, Chi-Square test is used to find that whether the standard deviation of the sample predicts the value of standard deviation of population or not. That is also based upon the significance level. This value is known as, is denoted as alpha here. So, this is the probability. I have probability for Chi-Square here. So, this is skewed data. So, I will try to solve this using a numerical, using a problem here. So, precision interval for Chi-Square, I can just put it probability for Chi-Square 1 minus alpha by 2 less than equal to value of Chi-Square less than equal to Chi-Square alpha by 2, which is equal to 1 minus alpha. 1 minus alpha is this probability I am talking about, this big area, okay, this big area. So, if I put this relation here and put the value of variance, so then I can put this Chi-Square probability for the variance would be the then ratio of the degrees of freedom into variance for sample over Chi-Square value for alpha by 2, and this is again on this side also I can have degrees of freedom variance sample divided by Chi-Square for 1 minus alpha by 2. This is a general formulation. So, the value of alpha, if it is let me say 5%, alpha by 2 will be 2.5%. So, we can consider it for any limits. So, before taking the example, I like to tell you the significance of Chi-Square distribution. Chi-Square distribution is most widely used for the test of associations, which is a non-parametric test. Therefore, it can be used for nominal data too. It is a test of statistical significance widely used bivariate tabular association analysis. So, typically when we have a hypothesis where we whether we need to see that whether or not the two populations are different in some characteristic or aspect, or their behavior is based upon two random samples, this test procedure is known as Pearson Chi-Square test. The Chi-Square goodness fit of test is also used, which is an observed distribution that conforms to any particular distribution. Calculation of this goodness of fit test is by comparison of the observed data with the data expected based upon particular distribution. So, we will not move to that tangent here, but just we need to compare two samples based upon their standard deviation, or we need to compare our sample to the population. Chi-Square test is used. This is the nutshell, this is the something in nutshell that we can, there is a takeaway for you people. So, Chi-Square is using the standard deviation to compare two samples sometimes, or to compare actually to compare two samples. F test is there. This is for comparing the sample standard deviation to the population standard deviation. So, I have this problem here. The 10 steel specimens are tested from a large batch, 10 steel specimens from large batch, and the sample variance is this. State the true variance expected at 95% confidence. If this kind of problem is there, we know the sample variance only, and we know how many specimens are selected. We just know the value of n is equal to 10, and we know the value of Sx, that is equal to Sx square, actually Sx square actually 4000 kilometer per meter square. So for this I have degrees of freedom is equal to n minus 1 is equal to 10 minus 1 is equal to 9, and he has called it 95% confidence interval. For 95% confidence interval, I will take the value of alpha. So here the value of alpha is 5% and alpha by 2 is 2.5%. So if I use this relation to solve this kind of problem, I can just put here mu into the variance for the sample by the chi-square value for alpha by 2 is less than equal to sigma square is less than equal to degrees of freedom into variance for the sample divided by chi-square values for 1 minus alpha by 2. Okay, I can just put the values directly here. It is 9 into 40,000 divided by chi-square value. I will just let you see how to find the chi-square value here. Less than equal to this is less than equal to 9 into 40,000 divided by chi-square for, this is chi-square for 2.5% actually. This is chi-square for 91 minus alpha by 2, that is 100 minus alpha by 2 is 0.025. This is chi-square for 97.5%. Okay. Now let us see the chi-square table. The value first is we need to select this degrees of freedom is 9. So this is the row that is selected. So we have chi-square distributions for different levels of significance here. So for 0.025 the value is 19, okay, and for 97.5 the value is 2.7. So these two values are there. This value is 19 for 0.025, it is 2.5%. For 97.5% the value is 2.7. So let me try to put these values here. For this value is 19. For this the value is 2.7. Here said state the true variance expected. So the precision interval for the variance is, if I calculate this, this is 18,947 is less than our variance, the precision variance for the population, and if this is less than equal to 133,333, I can put the units for the variance as well, kilo m plus by m square whole square, because this variance I have taken square at 95%. Okay. Now this precision interval about the variance due to random chance, then as n becomes larger, the precision interval narrows as s approaches our sample approaches the population. So this is the way to find the precision interval for our variance if it is required. Next and the last part in this presentation is data outlier detection. Sometimes we have data outliers which are due to some assignable causes or which are due to some non-random causes. So we need to find out where is the data outlier. There is a rule to find that. So data that lie outside the probability of normal variation incorrectly offset the sample mean value estimate, inflate the random uncertainty estimates, and influence a least square correlation. So statistical techniques can be used to detect such data points which are known as outliers. So, one approach to detect the outlier is Chauvenet'scriterion. Okay. This identifies the outliers having probability less than 1 by 2n. The probability of occurrence is less than this. So, to apply this criterion, we need to just find the value of z naught, okay, which is equal to the modulus of xi minus mean, as we did it before. So, z naught is equal to xi minus x bar by standard deviation of x, and the probability values for the data point, the potential data point, that is outlier. I can put here potential data point, that is outlier, that is calculated as 1 minus twice of the probability for the z naught if it is less than 1 by 2n. So, let me try to see this problem here. So, we have 10 measurements of a tire pressure made using an inexpensive handheld gauge. Test for the outliers using Chauvenet'scriterion. 10 measurements, okay, and we have this observation table here. Now, what we need to do to calculate these, we need to first find x bar, sx, x bar is nothing but sum of these values and the average of these values. So, x bar, that is calculated to be, x bar is 27 here, and sx is 3.8. So, let me try to apply that criteria, and n is equal to 10. Okay. Now, n is equal to 10, that implies 1 by 2n is equal to 1 by 20 is equal to 0.05. This means the outlier would be if 1 minus 2 into probability of z naught is less than 0.05. Okay. Now, we can calculate the value of z naught also using the relation that was given. We can find for the 10 data points, xi is actually our potential outlier. I can check it for this value. Okay. So, this is xi that is selected, this xi is selected here, x bar I know. So, 18 is my potential xi, and z naught I can find it using this value. So, that means for a xi is equal to 18, if I see my table, I will find, and using the relation given in the previous slide, I can find the value of z naught, that is equal to 2.368. Okay. So, 1 minus 2 into probability of z naught, which is equal to 1 minus 2 into, from the table if I see, probability of z naught would come out to be 0.4910. Z naught is calculated using this relation. Okay, this is the modulus here, z naught is always positive here. So, this probability is equal to 0.018. Okay. Now, this is the calculated probability for my xi 18, this is for xi is equal to 18, and this is my 1 by 2n. So, I can see here that 0.018 is less than 0.05. Now, this implies that this xi is an outlier. Okay. So xi is the outlier, 18 is the outlier here. Also we can check another outlier if we like, if we are interested, we can even check whether 24 is the outlier here. So in this lecture it might be quite heavy for you because we had new concepts and we have many mathematical relations, but don't worry, we will provide you with the notes to read more on this, like Chi-square distribution, what are the various applications, and we will put a quiz, and please do ask the logical questions as well in the forum. I will be very happy to respond to them, and we will meet in the next lecture. Just to recapitulate, I discussed the normal distribution, then about the application of normal distribution in real life, I did some numericals, then I discussed about the proportions and binomial distribution, then we had some information on Chi-square distribution to compare the variances of the sample and the population, then we saw a rule to detect the outliers. So we will meet in the next lecture, we will discuss the statistical parts in metrology further. Thank you.